Okay, hello, hello. Oh, um, good afternoon, good afternoon. Hang on one second here, just write something. Good afternoon. Oh, thank you. Thank you, Kaya. Good afternoon, Kaya. Thank you, Genesis. Good afternoon, Genesis. Oh, thank you, Kaya, twice. Oh, wow, I love it. Many points, many points. Submit for points. I love it, Kaya, and for the tag for the chat as well. So, good afternoon, Genesis. Good afternoon, Gabriella, who's also a video star in general. No expectations. I mean, no pressure. Awesome, guys. Thank you. Good afternoon, Ariana. Thank you for the chat. Good morning. Good afternoon. Good afternoon, Brandon. Good afternoon, everybody who's coming in right now. We'll get to, oh, good. Oh, and I like that, Skylar. Thank you, Skylar, for the avatar. You should submit for points for that. Um, and again, if you guys don't know what I'm talking about, you should ask me. And there's two different portals, one for avatar and one for animated avatar. The animated means the kind of thing that Kaya's doing right now, regular avatar. They're each points. But the one that Skylar's doing is like avatar, and the one that Kaya's doing is like animated avatar. Okay. Good afternoon, Joran. Joran. Good afternoon, Brandon. Oh, quick thing too. Sorry, this is not to embarrass you. Brandon, you may want to check your this is not a criticism, but just check when you get a chance, check your Google Drive storage because I there's a lot of work that you have turned in and I know it, but it's not allowing me to send you back feedback or grades or whatever because I think your storage is full. So just check or and talk to whatever, send me an email or just so that you get all the credit you deserve or and all the feedback you deserve. I think again, this is Brandon, just a personal thing to Brandon. Oh, okay, great, thank you, and you just got points for that. Submit for closing a conversational path. Honestly, great. Um, Andre. Good afternoon. Thank you for saying good afternoon, Yaneli. Good afternoon. Awesome, awesome. Why am I still bumping over pronunciation of people's names? Because my name is Yaverbaum. That's why. Okay, we're gonna get started. Also, please note in the chat quickly, we're in that stage now. No new work for you guys. You're trying to catch up and plug holes wherever you have them. You're trying to understand the material as I'm catching up to it. You're being very patient and waiting for your midterm exams back, which are not forgotten and which are higher priority than it may seem. I'm struggling a little bit. We're all struggling at this time of year. We're all going to be patient with one another. I really appreciate it. And I know it's hard to not have exams back. You will get them, but thank you for your and you'll know the minute I'm certainly not holding on to them to um on purpose. But okay. So thank you for your patience. It's in the chat. So what we're going to continue to do now, we're going to continue to analyze Newton's law force problems, specifically in the context of trying to help with your lab. Number 5. Let me be clear. Oh, wait. Oh, great. Direct chat person. Awesome. Wow. Okay. Wait, someone else is here. Okay. Um, So to be clear, like what we're talking about today, I'm trying to sort of analyze the situation in your lab 5, like for you or with you. I'm trying to do two things, but like the reason you have lab 5 is that it's a very, I think, a very demonstrative, vivid, challenging representation of a Newton's law force problem. So, first of all, to be clear, one of the reasons you do that lab is it puts together a lot of Newton's law concepts that are often put together on the final exam, which eventually we have to worry about. So, number one, just so that you know, everything I'm saying right now, all these procedures about solving Newton's law problems, they're all general procedures that are that always work and that would work if you have a problem of this kind on your final exam, which you will. But then also, I'm trying to do it through the lens of specifically helping you with your lab report on Lab 5. Okay, so anything I can do to make your life better and more clear in your lab responsibilities on this terrific, right? But it's for both purposes, like whichever one you like better. You're ultimately everything I'm saying about the lab or about to say about lab 5 is just true in general about problems involving forces. Uh, just the lab has interesting implications of that. Um, so bear that in mind as I continue with the procedure today. Um, um, but let me make sure that we are on the same page. Oops, sorry. Hello. Okay. Let's make sure that we are on the same page. Um, lab 5. So lab. First of all, remind me in this particular section, I believe, do you have in this section? In this section, you have Professor Walters for your lab instructor. Yes, Professor H. Walters, correct? I'm looking for some chat feedback here. Do you have Professor Walters for your as your lab instructor in this section? Yes, thank you, Kaya. You just got points for that. Please don't forget, you can totally submit that for points. Okay, great. So you have Professor H. Walters as opposed to Professor J. Walters, who may or may not totally be her husband, and may or may not have taken this class with her many, many, many years ago, and may or may not have had their first lab report read out loud at their wedding as part of a toast. May or may not, just saying. But okay, so you, Professor H. Walters, that's awesome. And thank you for catching that, Gabrielle. Yes, totally true. My favorite story ever, honestly. And oh, and one last thing, Professor H. Walters and I just can't resist. I love them so much. And their baby just turned 1 year old and they just sent us pictures. But I mean, they're the cutest ever. Sorry. But they were John Jay students a long, long time ago. They met. I used to want to believe they met in physics class. Not true. They met in chemistry class, which is sort of more perfect. But after they met in chemistry class, this is true. Okay. I don't know. You don't all know both of them, but they both exist. After they met in chemistry class as John Jay forensic science students, after that, literally they aligned their schedules so every single class they took in the forensic science major, every single class from their sophomore year or whatever, all the way through graduation, they took together with one exception. It doesn't matter what the exception, like, okay, I don't know about you guys. I can barely make my own schedule as a student. Like it was hard enough to get through school with a schedule that worked for me. They literally aligned their schedules so that they were in every single class together until they graduated. And they like worked on everything together and they were a great team. And then they got married and blah, 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 blah. So you see, John Jay, just when you think John Jay can't do anything for you in your life, like, oh, and then they both got jobs at John Jay. Anyway, okay. Yes, it really, yes, thank you. Okay, so there's hope for us all, you see. Um, Okay, so if you have Professor H. Walters for your lab, here's my next like serious question is, I'm assuming you're in the middle of your lab 5. That's the lab where the thing goes up the inclined plane and then comes down the inclined plane, right? Like that's lab 5. I I assume that you have not yet turned in a formal lab report, but that at some point in the future, a formal lab report is due, as far as you know, on lab 5. Can you confirm or deny? Like, is that sort of like true? That lab 5, like the slow down lab, the thing that where the thing goes up and then comes down. Am I correct that that's sort of what you're in the middle of now, or at least even if you're past it, that you have not turned in a formal lab report yet on that lab? Is that correct? Yes, correct. Thank you, Gabriella. Okay, awesome. And thank you for the beautiful love story thing, Alfred, especially for a guy who has such a crazy avatar. I'm glad to see Alfred. Don't see, never underestimate the complexity of human beings. Like he's got that avatar, but he can appreciate a beautiful love story. So what are you guys saying? I mean, okay, so good. So, all right. So lab 5. So I'm here to try to help with your lab report on lab 5. Like I don't, obviously everybody grades things differently and all of that. Like I'm not the one grading it, Professor Walters is, but it's not an easy lab. I'm here as usual in a way to give you answers. Like even what you're seeing right now on the board, in a way, is a big part of like the answer to the whole lab. I don't mind, and she's giving me permission. I don't mind like giving you answers, but it's like everything else, like my exams and stuff. The whole issue is like, why are the answers the answers? How do you understand the logic. How do you get there? So that's what you want to sort of hopefully join with me today in trying to unpack and understand. So hopefully this will all make it easier for you to write your lab reports or help each other. But you can't just like literally but if you just like copy this information, I don't think it'll work out that well. So I'm going to ask you, there's going to be a little class participation encouragement here to make sure that I'm actually being helpful or that we're on the same page. And you tell me when I'm going too slow or too fast in this discussion, because I don't know exactly what you understand and what you don't from lab. Right? So if I'm overemphasizing something that's already obvious to you all, put it in a direct chat. Just say, yeah, we got that. Could you get to the part where? Okay. And I will, or vice versa. But here we go. So lab 5 that I'm talking about. Well, in fact, okay. Lab 5 is a special case or a specific interesting case of what we generally consider to be a rough inclined plane. Inclined plane meaning it's like a ramp on a slant, right? That's what inclined plane means. Very standard, important piece of apparatus in physics. And it's rough, meaning it's realistic. Like actually, it's not perfectly smooth. It's not an ice hockey rink. So friction does play a role in the lab. And as you may have already come to understand, in this lab, friction doesn't just sort of play like an incidental role. It plays a very big role. And it's a big role that makes all the difference in the calculations in the end. It's not like a distraction. It's like the central point, the friction, right? So let me first remind you before we go any further. Now, again, all of this, the whole lab is supposed to be a big sort of hard example of a situation where we put together a lot of elements from forces and Newton's laws from this whole topic, right? So everything I've been saying for the last week about how to solve Newton's law problems, like including the homework problem, they're all sort of one element at a time. And then the lab is putting together many of those elements together at once. So one of the elements that is involved in the lab is the element of friction. So let me just remind you briefly how we understand friction. First of all, just to be clear and honest, in case you're going on in physics at all, or you're going into criminalistics or something like that, you should know, as a matter of reality, that there's really two cases of friction in the world. And the logic is the same for both cases of friction, but the numbers are a little bit different. Like friction can do one of two things. Friction always occurs when two surfaces are pushing against each other. Two rough surfaces are pushing against each other, right? That's what we keep saying. Friction occurs when two rough surfaces press against each other. The reality is that friction can occur either when one surface is actually rubbing or sliding along the other one. That's one case where we call kinetic or sliding friction, when the surfaces are actually in motion relative to each other. The other case is when they're not in motion, but something is trying to get one of them in motion. Like the other case of friction is when two surfaces are stationary relative to each other, but there's a net external force on one of them attempting to pull it along or push it along. And there's a kind of friction that automatically comes into play to hold things together. So the reality in life is that one kind of friction called static friction will hold things together even until it no longer can, until it fails, until the net external force that's attempting to move one object succeeds in overcoming the maximum possible force of static friction, at which time that friction fails, and then the objects start rubbing or sliding against one another. And then what kicks in is called kinetic or sliding friction. What I'm trying to say, first of all, I'm just telling you this so that you know the more honest truth, that friction can come in one of two varieties: the static case that holds things together, or the kinetic case that slows down or resists or opposes the moving of one thing relative to each other. It's if surfaces are rough at all, then one will apply until it no longer can, and then the other will apply. Like if surfaces are rough at all, then static friction will hold them together until it no longer can, and then kinetic friction will slow down their motion relative to each other. So it's always one or the other at a time. And each one has its own roughness coefficient. Like there's a mu for the static case and a mu versus a different mu for the kinetic case. It's always either one that's acting or the other at a time, never both at the same time, and never neither if the surfaces are rough at all. Okay. So it's one or the other. In fact, technically, it's like one and then the other. Now, once we get to so I want you to know that there's two cases of friction. There's F sub S, which is less than or equal to mu sub S times the normal. And then there's F sub K, which is equal to mu sub K times the normal. Now, once we get to the lab, and it's possible I might say more about the static case later, and we might have more problems to solve about it. And if we do, and we could talk about it on the final, whatever. But now in the case of the lab, anytime you're analyzing this lab, the marble is always in motion relative to the track. In the lab, you have a marble that goes up the track, the rough track, and then it comes down the track. At any given moment that you're interested in this lab, the marble is always in motion. So from here on in, everything I'm going to say today about the lab is like totally just the kinetic case. I'm not worried about, like the static case is not occurring during the lab. So I'm only going to talk about the kinetic case from here on in today, and therefore I'm going to drop all the subscripts. I don't need to have a K or an S making a distinction anymore because there is no distinction. There's only one kind of friction app. So from here on in, I mean the one kind of friction where the things are moving, and that's it. Okay, that's one thing I want to make. So stop me if that's not clear. Okay. Right. So that's what this board says. So in the case of our lab, where one surface is always in motion relative to the other, we are always dealing with one type. God, that my handwriting, Lordy. Blame it on the don't. So in the case of our lab, when one surface is always in motion relative to the other, we are always dealing with one type of friction. Hence, we will drop the subscripts. That's what this says. Okay. Oh, I'm looking at the chat. Good. Oh my God, that's such a great question. Okay, just a quick sidebar here, just because I love the parts. First, okay, so someone's put in the direct chat, so I'm not going to mention their name, but they should praise themselves. They should also submit for points for this. Okay. And I'm going to repeat the question because I think it's really interesting. So someone in the direct chat said, is the static friction the reason for static shocks? Now that's such a great, I mean, talk about someone who's paying attention and who's trying to link physics theory or physics class to real life. Like, thank you, seriously. Now the answer is no, but it's still a great question. I'm going to take a moment on it. Static friction is called static friction because the two objects are static. They're stationary. They're stable. They're not moving. They're at rest relative to each other. Okay. Static shocks are different, but the reason they're called static shocks is because the shocks that you feel, like if you like rub your socks against the carpet and then you touch the light switch or the metal light switch or something like that, right? That or like you pick a sock out of the dryer, like right after you turn off the dryer and then you get a shock, like that is called a static shock. And it's not a coincidence. It's called a static shock because of the electrostatic force that exists between the electrons on the outside of the sock and the outside of your finger, or in the case of the light switch, like the outside of the light switch and the outside of your finger. Like the static shocks are from an electrostatic force that automatically exists between electrons or protons, but in this case, between electrons. And that's not a crazy question at all. Let me say two quick things about this. Number one, so it is different, but number one, that's totally something we're going to study in depth in Physics 204. So this is not a distraction or like irrelevant at all. We will study the electrostatic force between electrons and between protons and electrons in physics 204. That's number one. So it's called, and it's called static. It's called electrostatic because it's a force that exists between electrons even when the electrons are not moving at all. Like the electrons don't have to do anything to exert this force on one another. It's called static because even if the electrons are just sitting still, not trying to do anything, they will automatically repel each other, like you know from chemistry. So it's called the electrostatic interaction because it doesn't require any motion for it to occur. It's a fundamental force, really important and really important for physics 204. So not at all like the tangent in the long run. But the other reason this is not a tangent question, why it's a brilliant question, even though it is a little bit different, like friction and electricity is a little bit different. Not only do they both have the word static in it because things are like at rest, but also honestly, in the end of the day, I'm not trying to just like make somebody feel good or just compliment somebody here. The fact of the matter is, the real reason that there is friction between one object and another, like the marble and your track or whatever, or my two hands. The actual reason there is friction between my hands in the end of the day is because the electrons on the outside of my hands are resisting, the outside of one hand are resisting the electrons on the outside of the other hand. They're exerting repulsive forces like you learned about in chemistry. And it's the repulsive forces that are saying electrons, get away, get away, get away. And that's what's causing the resistance to sliding in the long run. Like in the long run, at the end of the day, the macroscopically observable phenomenon of friction is actually coming about because of microscopic phenomena occurring known as electricity. So really, the person who asked this question, it's an amazingly awesome question. Because even though it was just really the words that make it sort of sound like the two things are similar, and even though on the surface, right, one is mechanics, physics 203, and the other is electricity, physics 204. But the fact is, they're ultimately linked. Below the surface, it's all happening. It's all happening because of electrons, ultimately. So yes, super related. The person who asked that question, I just want to say again, the person who asked that, oh, that's awesome. Okay. So the person who just asked that in the direct chat and just gave a little follow-up, like there's a million portals you should now submit for points to, honestly, for the question, for the follow-up, really. And those are the rest of you. Again, I'm going to go back now, but I want you to know that could be you as much as that person. This is not a distraction. We're here to learn and see how the world is working. Like, okay, like, and whatever. I can't encourage enough. The only thing that goes on your exams are the things that we learn in the class. I don't put things on the exams that are just like in a textbook somewhere, even if we never got to them. So if we talk about a little physics for 5 minutes because one of you is actually like really engaged and making connections, it doesn't slow you. It doesn't like mess you up on your, I hope you understand that. Like, anyway, great question. Okay. All right. So, and hopefully that will help you a little bit when we get to physics 204 and you have exams. But anyway, all right. So moving on. All right. So, okay. So the next board. All right. So this is me over elaborating now. I can move on now. I'm just saying like, we're now just talking about one kind of friction. So I'm going to drop the subscripts and say that the magnitude of the kind of friction that we're dealing with in the lab is the magnitude of the mu times the magnitude of the normal force. Now, that's magnitude. I said this on Wednesday, but let me like quickly review or remind you like what that's all about. Remember, this phenomenon comes about for two reasons. This phenomenon that it is difficult, well, it ultimately comes about because of electrons, because of what somebody just had, but macroscopically, this or the resistance to your marble's motion along the track, that the sliding resistance between two surfaces comes about when two rough surfaces press against each other. This is the key to the whole thing, right? Like, why is there friction? Because a surface that's rough, when it presses another surface that's rough, if it's actually rough, if you zoom in and look at all the bumps and like the hills and valleys of the surface, which are really electrons and electron gaps. If you look at all the bumps and valleys of a surface, when they press against another surface, the bumps and valleys lock into each other like teeth of a comb. So the harder you go like this, the harder it is to go like that, right? This is called the normal force. The more of this there is, the more of that there is, as long as the surfaces are rough. If the surfaces are not rough at all, then this doesn't affect that because there's no bumps and valleys. So this friction along the axis that is parallel to the plane of contact comes about for two factors: the roughness of the two planes and how hard they're pressing against the plane of contact. Pressing against the plane of contact means pressing perpendicular to the plane of contact. That's called the normal force. Right? This is called the normal force. Normal is not about y or x. It's about perpendicular to the plane of contact. So if the plane of contact is, if this is the plane of contact, then the normal force is that way. If this is the plane of contact, then the normal force is that way, right? Right? So the normal force is a force measured in newtons. You multiply that by the amount of roughness. The amount of roughness is just a coefficient. It's just a number between 0 and 1. Right? So the roughness is just a number that has no units at all. The normal force is a force measured in newtons. So what we're saying in the end is this force measured in newtons is some like percentage or some scaling factor, some multiplier on this force. The harder this force, the more this force. And the rougher the two surfaces, the more percentage or the more this force gets multiplied to make this force. Friction in the end is a simple multiplication of a roughness number called the coefficient of friction times the normal force, a magnitude of force measured in newtons. If that does not make sense to you, please stop me or tell me. But and I'm saying that logic is true for any case of friction, whether it's static or kinetic. Just the difference is if it's static or kinetic, like you'll have two different coefficient numbers and a couple other subtleties, but the logic is the same either way. So first of all, the force of friction is mu times the normal. That's the magnitude of the force of friction in life in general. Then second of all, the direction of friction. What's the direction? Well, it's sort of obvious and sort of not. I mean, it is, in simple cases, it's exactly what you'd think it would be. The direction that friction points, well, let's be relativistic about, like, let's realize force is a relation, force is an interaction between two objects. So the direction of, so this is what this says. So this is, force is friction is a force. Force is a vector. So it has magnitude and it has direction. What I'm explaining on this board, I'm just technically reminding you on this board, is the magnitude and the direction of friction. So the magnitude is what I just said, mu times the normal. The direction of the friction exerted by surface A onto surface B, this is totally illegible. That's why I'm reading it out loud. The direction of friction exerted by surface A onto, this is supposed to say, onto surface B. I don't care what any surface A and B are any surfaces. The direction of friction exerted by surface A onto surface B opposes the motion of B relative to A. That's what this is trying to say. It's a relative thing, like everything, like a lot in physics. Wait, okay. Meaning, like, example, like the friction from the bottom acting on the top opposes the motion of the top relative to the bottom. So if the top is trying to go to the left relative to the bottom, then the bottom will exert a force on it pointing to the right, like just like what you would think. Or if your marble is trying to go down the track, then the track will exert a friction on it going up the track. It always opposes so the friction from one surface opposes the motion of the other surface relative to it. It's relative to it. It's not relative to the universe. I don't know what that would mean. And more particularly, it's like not, well, what it's not, well, I'll just leave it at that. Okay. So in the case of so sometimes that can lead to some interesting subtleties, but in the lab, it's exactly what you would think. If the marble is going down the track, the friction is going to point up. If the marble's trying to go down, if the marble's going up the track, the friction from the track will point down. And I hope that's clear. And I think that's what you would think. And someone's here. Hold on 1 second. Sorry. Okay. Um, that's like, but that's true for like any future problems you might do for me or for homework or for exam. Okay. That's how friction works, magnitude and direction. So now we're going to start applying this to the lab. Okay. So here I'm just like now I'm trying to back our way in and review for you what the lab situation is and how friction is going to apply to it. And we have 45 minutes left for good or for bad. So in our lab, it says in our lab 5, friction from an inclined plane, the ramp, the tilted ramp, off in physics generally called an inclined plane. Friction from an inclined plane opposes the motion of a marble moving along the plane. That's just what I'm saying, right? In our lab, the marble, all right, now in our lab, and you're going to correct me if this is not what you understand or not what you experienced or something. I believe that in your lab, you flicked the little lab and it went like up an incline, it went up a track until it ran out of speed. It ran out of speed temporarily, and then it like came back down and it came back to where it started. And you started your stopwatch once it was in motion, and then you stop your stopwatch when it gets back down to that same original point, right? So it goes up and then down. It makes a round trip, a natural round trip in your lab. Yes, right. So we're okay. So that's what happened in your lab. But the question of your lab, I believe, and I'm going to stop. There's just an early warning or pro tip for people who are still with me. I'm going to stop in a second and start asking you a couple of questions about your lab experience. So, like, buckle your seatbelt or whatever. So I believe that the ultimate, I mean, there's a number of questions that the lab asks you, but I think the big ultimate research question of the lab is assuming that we flick this marble and it goes up and then it comes back down, the question is, how does the up trip time compare to the down trip time? Like, are they the same? Is the up trip longer, bigger, or is the down trip bigger? Like, that's the question of the lab, I think. Again, there's some other questions like what is the coefficient of friction, which you're not given, but you can ultimately get. But I think the central interesting question of the lab is how do the two trips compare? Now, yeah, so this is a situation, right? This picture, and I'm going to stop in a second and ask you a couple of things, but this is a picture. This is like what would be step 1 DFP, diagram fact pattern, right? This is, please note, this picture that I've drawn here in yellow, this is not a system schema. It's not a free body diagram. It's not a problem solving diagram. It's not a step 4 kind of thing. It's a step 1 kind of thing. It's just the situation. And the way I see the situation is that we flick something, we flick a marble, so we give it an initial velocity that isn't 0, right? Like we set it in motion. It goes up this rough track. It's a track that's that's inclined at some angle theta. Theta is not 0. It's a ramp, that's on a slant. The track is rough. So mu is not 0. Like, I don't know what these numbers are, but I know they're not 0, and that's crucial for the whole lab to occur. So mu is not 0. V naught is not 0. Theta, I should say, is not 0. Right? And so this marble goes up the ramp at some initial velocity. I could even say, initial velocity that's greater than 0. I could, maybe that's even, is that even, yeah, I'll leave it at that. So it goes up with some non-zero initial velocity. Presumably it gets slower and slower and slower until it reaches a moment where it runs out of speed entirely, has a speed, instantaneous velocity of zero, and then it starts coming back down, gaining speed, gaining speed, gaining speed. And when it gets back down to the original spot from which you launched it, you stop your stopwatch. I should also say that you start your stopwatch once the thing is in motion from your finger or whoever flicked it. And there's gravity involved. Gravity is always pulling down, straight down to the center of the earth, right? So these are all the facts of the problem. And the ultimate question is, how does the time for up compare to the time for down? Now, before you look at it, here's my question to you. I want an honest answer. It doesn't matter. There's no right or wrong, but I do want an honest answer. If this is more or less what you did, let me ask, first of all, honestly, did any of you or did you make a prediction before you did the lab? Can any of you recall making a prediction as to whether it would take more time to go up or more time to come down or equal times? Oh, that's yes. That's Alfred. Thank you, Alfred. Yes. Awesome. First of all, that's points. Thank you. Thank you. And then second of all, if you don't mind elaborating, or anybody, Alfred, and but again, also, maybe this is also true in 204. Like, notice how Alfred just said yes, which is like super helpful. Great. And I was just going to say, beautiful, beautiful. All right. And I was just going to say, even though if Alfred says yes, there's no reason that it's not like a competition. Like if someone else said yes, even 2 minutes later, like Brian, if someone says yes 2 minutes later, they get points also. This is not a competition. I cannot stress that enough. Like the more I feel like people are with me, the better we can all be at like learning and teaching this. So it's not a race to who gets to the chat. You notice there's not one portal for being the first person to be in a chat ever. So okay, so thank you, Alfred, and thank you, Brian. Now, Brian even just also answered my next question, which other people still can, even though we already did. I'd love to know. Any and all of you. Like, oh, thank you, Gabriella. I love it. See, you guys are so visit me sometime at 4.61.05. Sometime if I'm ever there. Oh no, great. And I'll see you in 204 and I'll write you a recommendation for a job at having bad voices. Okay, so thank you, Brian. Thank you, Alfred. Thank you, Gabriella. Yes, now at least two people are telling me, and I'll take it that Alfred is telling me that they predicted that this is very important for everybody. You guys, Brian and Gabrielle specifically, they made a prediction in the lab that I want to be very clear. Absolutely would have been or was my prediction as well. It's an honorable, admirable, totally intelligent prediction. I too, not only would I did before I made up this whole lab on purpose for this reason, like obviously many years ago. Like I too, stay with me for a second. If you predicted, and especially if you put in the chat that I predicted that this thing would take more time to go up than it would to come back down, that is so smart and reasonable. Like on every level, that's what I would expect too, right? I mean, going up is harder than coming down. Let me be more specific. When you're on your way up, you're slowing down. There's no question about that. Even in this lab, even with friction, on your way up, on the ball's way up, it is slowing down. It starts with an initial velocity that's bigger than zero, or initial speed that's bigger than zero. It is losing speed until it gets to the top, at which point it has zero speed. Then it comes back down and it's gaining speed, gaining speed, gaining speed. So on the way up, you're slowing down. On the way back down, you're speeding up. I would have totally thought that that would mean, well, I mean, presumably, if anything, then on the way up, you're on average, you're going slow. And on the way back down, you're going fast. Like it's harder to go up than it is to go down. So I too would have totally expected that going up would take more time than coming down. However, if you did this lab carefully, and if you had a very well, let me ask, whether it's Gabriella or Brian or Alfred or anybody else, like what did you find once you ran the experiment and you did a bunch of trials? Like honestly, what did actually occur in the lab? Awesome. Perfect. I love it. Thank you, Gabriella. She's yeah. Oh, and then private chat. Okay, awesome. Right. Awesome. I love the way that was not the case. She says it was quicker going up. Yes. And then I see in the private chat, yes, it is down trip that is longer. Okay, so folks, that's all correct. So first of all, okay, we're in the same page here. All the people that just put anything in the chat, like there's so many places you could post this for points. You can post it to the place that says for right or for wrong, because you just answered a question. It doesn't matter if it was right or wrong. You get points for that. You also get points for the follow-up, closing a conversational path. But also now feel free, all of you, to post in to post in the portal that says wrong, be really, really wrong. Not that you're being wrong now. You're not doing anything wrong at all. But your prediction, it turns out, was wrong, just like mine was. That's why this lab is worth it. And it's not a mistake. And I think it is a surprise. I think there's something to learn here, but it's not an exception or a technicality or weird black magic or something like that. Like, it seems like slowing down should mean slow and speeding up should mean fast, but somehow this thing takes more time to go down than it does to go up. And I'm sure you notice, as long as you do it sort of carefully and you do a bunch of trials and you average them, right? But that's just it. You just have to be sort of careful. That's it. There's no fancy equipment in this lab. I'm sure you notice it's pretty primitive, right? It's just a marble on a track. There's nothing special. The only special thing is that there's friction involved, and friction is like reality. So the issue of the whole lab, and the thing that I now have 34 minutes to explain, is like, why? What is going on here? And this is a really good example of physics, folks. Everybody, like, again, thank you for participating. Thank you for paying attention. Honestly, but like, here's why we're all paying attention together. Like, why? And I love this lab. Like, I made this up like 30 years ago because one day it occurred to me. I was just like playing around and stuff. And I was like, wait a sec. Like, wait, if all this stuff that we're saying about friction and everything is like really true, wouldn't it be the case that something would go? And I was like, no, that can't be right. That's like the dumbest thing. What? That can't be right. And then I literally just tested it. I didn't even, when I first tested this, I not only did I have primitive equipment like you, but I didn't even have a stopwatch. When I first was like, wait, that can't be right. Of course, when something's going up, it slows down and it would take longer than coming down. And then I tested it a couple times and just looking at it with my eyeball, I was like, oh my God, it's going like, now it's more exaggerated, more clear, the slower the like shallower the angle, for reasons that you'll ultimately see. It's more clear the shallower the angle. It's more clear the rougher the surfaces. It's even more clear if you slide something rather than roll it, which you can do. Like, but it's really weird because once you actually look at it, I don't know if any of you notice this in the lab. Once you actually know what you're looking for, once you open your mind, you can notice that this is true even without precision timing. Like, to your eyeball, you can actually just see that it goes, but you would never notice that if you're not looking for it. You would, and I would have sworn that I had always seen it the other way because it seems natural. So this is the thing with physics always. Physics is here. It's not meant to be BS. I mean, physics is meant to start with things that are statements, observations about the world that are intuitive and experiential. It is about the real world. It is about how we see and experience the world on an intuitive, sensible level, whether we're like calculus geniuses or not. It's not meant to be some obscure, weird thing that's just about like Smurf Village. It's meant to be about reality. But the thing about physics is that the more you do physics, the more closely you look at reality and the more you think about it, the more your intuition for reality gets refined. And the more your mind gets open to things that you wouldn't have expected about reality. In the end of the day, the reason physicists believe in really surprising things like black holes or big bangs or twin paradoxes, if you've ever heard of that, or stuff like that, is not because we want to be weird. It's because the more seriously we take the things that aren't weird, the more seriously we analyze and zoom in on stuff that is intuitive, the more we develop our intuition and realize that there are really surprising aspects of the universe that follow logically from the really unsurprising things. Okay, so everything in physics is a mini proof or derivation that starts with something intuitive and then leads us to some kind of slight or large surprise. This lab, I believe, is a slight surprise. And I'm going to show you now. I'm going to stop yammering. I'm going to do the math with you. But the goal of this lab is not just to know the result or whatever, or to memorize a bunch of pictures. The goal is to show how if you take force diagrams seriously and the force equation of Newton's second law seriously, if you go step by step and analyze it seriously, you eventually see that, in fact, we would expect, ultimately, once we get used to all this, we would expect that something going up a rough surface would take less time than something going down. I wouldn't have initially expected it any more than you. But once we actually walk through all the diagrams, it actually makes refined sense. And that's your goal, my goal with you for the next 30 minutes. And you stop me when I'm not, and maybe it already does. But your goal is to understand this enough to see why you originally predicted what you did, but why in the end of the day, now you can show why actually it's not an exception. It is the rule that something should take more time to come down a rough inclined plane than to go up it. And that's why the lab is called slow down. Okay. In other words, all right. So what it says in white at the bottom of this board. So I will keep going. Thank you again for participating, though. What it says in the white is, despite typical predictions, the object will come back down slower than it went up. Why? So the question is why? So here we go. So now we're going to compare an arbitrary moment in the ball's upward journey to an arbitrary moment in the ball's downward journey. Arbitrary moment. We're going to do it the way we always solve any physics problems, any force problems. We're going to compare so it's all about comparing up to down. So we're going to compare an arbitrary moment in the up versus an arbitrary moment in the down. And we're going to do it in the standard procedure, which means we're going to draw a system schema. From that, we're going to draw a pure free body diagram. From that, we're going to draw a component free body diagram. From that, we're going to do F net equals ma, i.e. Newton's second law, one axis at a time from our component, our axis free body diagram. That's the procedure for all force problems, whether it's this one or one on your homework or one on the final exam, right? That's the procedure. And just to be clear for a second before I move on, we still have our 5-step problem-solving procedure for problems in general in physics. It's still a 5-step procedure, but specifically Newton's laws have their own like sub-procedure, which is very comfortable and reliable to follow. So like, how does this all fit together with 5 steps? We're still doing the 5 steps always. You still draw a diagram and fact pattern like I already did, like back here, or right here. That's like step 1. Okay, and then step 2 is like, why is downward time bigger than upward time or something? That's like step 2, the question, right? And then step 3 is GDPs. What are the GDPs? F net equals MA. That's the GDP. F net equals MA is the GDP. Then we get to step 4, solving the problem. You can expand step 4, all the work expands into this sub procedure that I'm now going to show you. Okay, stop me if that doesn't make sense, but I'm saying everything I'm showing you now is like the zoom in or the expansion of step 4 when it comes to force problems. So that's why I'm like labeling the steps like A, B, C. They're all under step 4, if that makes sense. So step A, you draw a system schema. What is a system schema? It's a dotted circle for the mass, as you see here. Then you always draw a solid circle for the entire Earth because it's always there. And the entire Earth is always gravitationally pulling on your mass with one pull. So it gets one line. So system schema has the entire Earth pulling on your mass. Then after you draw entire Earth, and again, the procedure I'm telling you now, I'm trying to tell you, I'm applying it to your lab here, but it's the procedure that you would always follow for any force problem. It like always works, but here it is being applied to your lab. So then after you draw the entire Earth, you draw one object, one solid circle for each and every object that is touching your mass, right? You have Earth, because it's the only thing that affects without touching or interacts without touching. And then everything that's touching, you draw a solid circle. So what's touching your mass? The track. That's it. So you draw a track, solid circle. Now your track is a surface. It's a rough surface that's pressing against your ball. So like we said last week, to cover yourself in the possibility that the two surfaces are rough, you always draw two lines. One, right? Whenever rough surfaces are touching each other in the system schema, you draw two lines, one to represent this interaction and one to represent this interaction in case the surfaces are rough. Now, the surfaces are rough in this case. So both of those lines really are going to matter here. Like in a problem that we did last Wednesday, we ignored one of them because roughness didn't end up playing a role, but it is playing a role here. So there's our system schema. It's just Earth plus everything touching the mass. The only thing touching the mass is the track. So there we are. Now note that all the analysis I'm doing, and by the way, that's a system schema, whether the thing is going up or down, because system schemas don't care about direction or a plate or location or anything. So that's a system schema, period, whether the thing is going up or down. And notice, all these diagrams are meant to be each of these diagrams is meant to be a diagram of a arbitrary point in space and time during the experiment. So I have to be very emphatic about that. Like everything, that might sound obvious, but why am I like stopping to talk about that? Because I don't know why. Because there is a moment where your finger touches the ball. But that moment is before the experiment happens. Okay, your finger is not a force during this experiment. That's really important to know. A lot of people tend to think that it is. Like this is the easiest way to get things wrong in this lab or on a final exam or something is like, what is the role that your finger is playing? The role that your finger is playing is that it is providing an initial velocity to the ball. It is starting off, like, let me put it another way. Yes, you can't do this experiment unless someone touches the marble, but you also can't do this experiment unless you walk into the classroom and put your books down. Like, I'm not trying to be obnoxious, but like, there's a lot of things that have to happen in order to get this experiment going. All of those things are just that, things that have to happen in order to get this experiment going. You have to flick the marble in order to get the marble going. Once you flick it, once the marble has escaped from your hand, it now has an initial velocity and your stopwatch starts and the experiment begins. Yes, some people will flick the marble harder than other people will. That will be accounted for in the numbers. That will affect the numbers. It will affect the numbers ultimately as an initial velocity, right? An initial velocity, a precondition of the experiment. But it is not something that is occurring in an ongoing fashion during the experiment. Your hand does not remain in contact with the marble. So from here on in, once the experiment begins, the marble is never being touched by your hand again. That is never a force during the experiment. Very important to know. Do not put your finger in any diagram, any force diagram or any equation, well, or any force equation of this lab. And please do not think that the finger has anything to do with why this thing takes less time to go up than to go down. That is not the reason. Just to be okay, and people often think it is. So I'm just trying to say that to be so okay. So this is the system schema. There's no finger in the system schema. That's the system schema. Now we have to use that system schema to make a pure free body diagram. That means always, that's what we do. So we're going to go to step B, pure free body diagram. Notice the whole purpose of this is we're going to take each one of these lines and turn it into an arrow, a vector that has magnitude and direction in the pure free body diagram. So there's three lines here. There should be 3 arrows in our pure free body diagram, exactly 3. Again, sidebar, sometimes we might ignore one of these lines if we really believe that there's no roughness at all. If friction really, we're confident is playing no role, then we might ignore the line that means friction, but it's totally playing a role here, so I'm not going to ignore it. So there's going to be 3 arrows in my diagram, in my pure free body diagram. Now I'm going to say one more thing, sorry. Usually there's one system schema, one pure free body diagram, then you break it up and you make one component diagram. Here, the whole purpose of the lab is that we're comparing what something apparently different happens on the way up versus the way down. Because apparently, if you do all the data, you get that the thing takes a different time to go up than to come down. So something is different about up and down. So we're comparing up to down. So I'm going to do a pure free body diagram for up, and I'm going to do a pure free body diagram for down. And I think they're going to be different in an important way. Okay, so here we go. So for when the marble is moving up, here is my pure free body diagram. I've got the downward arrow for weight, for mg, for the gravitational force, right? That's that line that went to EE, the line that came from entire Earth. Always in every system schema, it becomes the force of mg in every free body diagram. The Earth is always pulling you straight down. And see, now we're caring about magnitude and direction. Now they become arrows, so I care. Mg, and now I no longer care what objects these forces came from. I just care about the mathematically useful name of the force itself. So the force of mg points straight down. That's in every single diagram ever. Then the track is pushing against the ball in two ways. One, against the plane of contact, and two, along the plane of contact. That's called normal and friction, right? Normal means perpendicular to the plane of contact. The plane of contact, according to my picture, the plane of contact is like this, right? That's the plane of contact. So the normal is perpendicular to the plane of contact. So if this is and this is why you have to draw this picture first. My picture, the track looks like that. Yours, the track might be going the other way. That's fine, but you got to show me which way, because in my case, if the track is going like that, then my normal force is going perpendicular to it, up and to the left. Yes, stop me if I'm not. So the normal force definitely is going the way it is whether the marble's moving up or moving down. The normal force is going perpendicular to the plane of contact between the track and the marble. And then friction must be parallel to the plane always, always. So friction and normal always have to be perpendicular to each other. So friction's along the plane of contact. But in the case where the marble is moving up, then friction's pulling down, right? We said that before. In the case where the marble is going down, then friction flips and is going up, right? So these two diagrams are identical, except that friction is going in opposite directions right? The normal and gravity are still the same either way, but friction has flipped its direction. Now, again, notice there aren't two different system schemas because system schema doesn't care about direction. System schema is just how you're identifying what the forces are in the first place by looking at what objects are touching your mass. But so this, one last time, this is whoa, hello. That, oh my God. Hello. Blame it on the chemo. No, I'm just kidding. That's not funny. Okay, so this is the pure free body diagram for an arbitrary point while the object is going up. And again, there ain't no finger in that diagram. And then this is the pure free body diagram when the marble is sliding down. Okay, so those are our pure free body diagrams. Now, what's the point of that? The point of that is we want to do F net equals MA. And it's like solve we're ultimately trying to solve for why is the time different for the two, and specifically, why is the time greater for the way up? Why is the time greater for the way down than for the way up? Well, where I'm heading with all this is the way I'm going to find out is I'm going to compare the two accelerations. In fact, let me say this since we've got 16 minutes left. Like, if the time on the way down is greater than which again is a surprise, but apparently can be explained. If the time on the way down is greater than the time on the way up, then that's got to mean that the time on the way if the time on the way down is greater, that means that somehow the ball is going slower on the way down than it is on the way up. And that is true. Let me say that again. The ball evidently is going slower on the way down than it is up on average, right? I mean, let me say this again. The ball is speeding up on the way down, It is speeding up on the way down, and it is slowing down on the way up. But slowing down and going slow is not the same thing. That's part of the whole point of like the whole first part of this course. Velocity and acceleration are related, but they're not the same thing. So the thing is slowing down on the way up, but evidently must be having a higher average speed than it does on the way down. If it's going right, it's going faster on the way up and slower on the way down, evidently. Hence the name of the lab, slow down. Um, it so how could that be? I don't know yet, but it must have to do with the accelerations. Is what I'm trying to solve for here with 15 minutes left. I'm trying to compare the magnitude of acceleration on the way up versus on the way down. If this thing is going faster on the way up, evidently there must be a greater rate of acceleration on the way up, a greater rate, a greater magnitude. Now that is confusing. I mean, I don't want you to be confused, but I want you to admit to yourself, if you don't like what I just said, you're good. Welcome to the club. I'm going to straighten it out, but let me say it again. On the way up, when this thing is slowing down, it must, it's slowing down, so it has an acceleration, right? Acceleration means change in velocity per time. Don't even think about whether it's negative or positive for the minute. Don't think about whether it's a negative acceleration or don't think about whether it's a deceleration or just think. There's a change in velocity. There's an acceleration on the way up, and there's an acceleration on the way down. Well, if on the way up, this thing is going faster on average than on the way down, then it seems to me somehow on the way up, this thing has a greater magnitude of acceleration than it does on the way down. Did I expect that? Does that sound like it makes sense? No, I'm going to say it again. On the way up, this thing must have a greater magnitude of acceleration than it does on the way down. Now, it must, if your data is correct. So why? How? Well, that's what I'm going to try to do. F net equals MA to get the A's and compare them. That's my goal here. So how do I do F net equals MA on each axis? Well, I have to do it on each axis. I have got to have arrows lined up on all my axes. I look at my pure free body diagram and I need to do more before I can do math because I look at the pure free body diagram or either one and I see that some arrows are not perpendicular nor perpendicular to other arrows. Like they're not all on axes. So I've got to pick some coordinate axes and line. I've got a picture, a coordinate system with an X and Y axis, and then make sure that any arrows that are not lying along those axes get broken up into two components that lie along. Everything's got to lie along an X or a Y for me to be able to do the math. So what I do, so this is the purpose always of a component free body diagram. If you have a pure free body diagram where not everything is along axes, you got to pick axes and break up anything that ain't along those axes. So I'm going to pick axes. Now, I'm going to follow the same rule that I said last week. But if you're really following all this, I'm going to follow the same rule. I'm not trying to confuse you. I'm going to follow the same rule, but you're going to see that the rule leads to a different outcome this week than last. What's the rule? What am I talking about? I'm saying the rule is when you go to make a component free body diagram, you got to choose a positive x-axis that aligns with the expected direction of positive acceleration. You want to line up your positive x with your expected positive a. That's what we said last week too. Last week when we were doing something like dragging someone, or you were dragging a box along a floor, and you were dragging it horizontally along the floor or along a table. So last week we expected the box to accelerate horizontally along the table. So we lined up, so we said, okay, fine, that's our x-axis horizontal, and that's our y-axis perpendicular to that. It was so sort of natural that it probably seemed like I was wasting your time even like saying that, like, duh, x-axis, y-axis. But now I'm saying, no, wait, the rule is you line up your x-axis with your expected direction of acceleration. Well, I'm on a track now. So I expect this ball to accelerate along the track on a slant, right? Not purely horizontally. I expect it to roll along the track. Furthermore, I expect the acceleration to point down along the track, whether or not the object is going, like whether the object is moving up or moving down, it's accelerating down. What do I mean by that? I mean, just take it to the limiting case. Take it to the old example. If you just throw something straight up in the air and it comes back down, remember, it doesn't matter whether the thing is going up or coming down. It's always accelerating down. When it goes up, it's slowing down. When it comes back down, it's speeding up, right? Like a normal, right? So if you call down negative, gravity is always producing a free fall acceleration of negative 9.8. Whether the thing is positively velocitizing or negatively, like that's subtle. But right, on the way down, you gain speed. On the way up, you lose speed. Either way, your velocity numbers are tending towards down. There's a better way for me to say it, but I'm not going to. Stop me if you don't. So therefore, I'm saying this marble is accelerating down the track no matter what it's doing. Therefore, I'm going to call down positive. I'm calling the direction of down the track positive. So I'm going to line up an x-axis. The positive x-axis, and this is my advice, like, could you do this lab and do it the other way? Yeah, but it only makes it harder, a lot harder. And often we even look at that at the final exam. Anyway, I'm suggesting strongly that you call the down along the track direction the positive x-axis, and therefore what's perpendicular to that, like what's up against the track, is positive y. Okay, so I'm tilting my head. I'm making my x and y axis tilted to align with the expectation of the acceleration. Therefore, with 9 minutes left, you notice now gravity, which otherwise looked perfectly well behaved. Gravity looked like it was just pulling straight down, but I'm saying now straight down is no longer good. It's no longer along an axis. There is no axis that points straight up and down. So it's gravity that has to be broken up, decomposed. Every other vector is either along the x or along the y. I mean, positive or negative. It's along one of those axes, but gravity isn't. So we got to break up gravity. So we've got to view gravity, mg, like the big downward pointing arrow is now the hypotenuse of some right triangle. Now you got to get used to that. I mean, I know you already like know this, but this is the jostling thing of the lab that people don't expect until they get used to it. Is that first, like I'm saying, right triangles, hypotenuses of right triangles don't have to be diagonal lines. Triangles can be turned. I don't mean that condescendingly. Like it threw me for a long time too. But even though gravity is vertical, it's the hypotenuse. It's being broken up into two legs that are perpendicular to each other. And one of those legs, okay, I've already filled it in on this slide, but like the thought process here is we're going to break up mg into its two components. One is mg sine theta. The other is mg cos theta, always. Whenever we're breaking up a vector into two components, one component is that, like, this is just like displacements, velocities, everything from the first part of the semester. When you take a vector and you say it's doing two jobs, it's got two components. One component is the sine component from SOHCAHTOA. The other is the cosine. The hard question is which one is which, and that is the hard question. If that's what you're struggling with, welcome to physics, okay? And that's what I'm going to try to quickly explain right now. But it's always, one of them is always sine and one's cosine. The question is which is which. So even though I've like sort of already filled in the answer here in yellow, here's the deal. Physically, what we're saying is gravity is pulling straight down to the center of the earth. But no matter what, but the ball is on an inclined plane going like that, going, you know what I'm going, sorry, going down into the left. So that means when the center of the earth is pulling the marble straight down, that really means it's doing two jobs. To some extent, the weight of the marble is sending it along the plane. And to some extent, the weight of the marble is keeping it on or against the plane, right? Just like southwest really means some amount south plus some amount west, right? That's what you said earlier with vector stuff. Now we're saying down really means down along some extent plus down against some extent. That's what we're saying here. The two components of mg, the sine and the cosine, whichever one they are mathematically, are the two fractions of the, like the marble has a weight, mg. Say the marble has a mass of 2 kilograms and has a weight of like 19.6 newtons. Some portion of that weight is sending it along the plane. Some portion of the weight is holding it against the plane. What portion? Well, it depends how big the angle is. If the angle is 0, if this thing is just purely horizontal, oh, then all of the weight of the object is just keeping it on the plane, right? I mean, if the plane is literally angle 0 horizontal, then all of the weight is keeping it on the plane. And none of it is sending it along the plane. You go to the other limiting case, if the plane's purely vertical, then all of the weight is sending it along the plane and none of it is keeping it against the plane, right? So in a way, that's how I know which one of these is sine and which is cosine. In a way, if you just heard what I just said, and if you realize that the sine of theta is always, the sine of 0 is always 0, then sine must be the component that's along the plane. Because sine of 0 is 0, and as angles get bigger, sine gets bigger. Sine is super, cosine is crappy. Or sine is super, cosine is counterintuitive. Like you can memorize that. Like the sine of 0 is 0, and the bigger the angle, the bigger the sine. That's just what everybody would think naturally. Cosine is the opposite of that. So as the angle gets bigger and bigger, the sine component gets bigger. As the angle gets steeper, more and more of the weight of this marble is sending it along the plane. That's the sine component. I'm trying to explain how I know which one is sine and which one's cosine. One way I know is because the sine of 0 is 0. And as angles get bigger, sine gets bigger. That's partly how I know. The other way I know, if you don't like that, if you literally just do the geometry out, if you do like alternate interior, like if you do two parallel lines cut by a transversal and look at the alternate interior angles or whatever, if you realize that theta, like when I say mg sine theta or mg cosine theta, I'm talking about the theta that you could originally be given in the lab, that you could originally know by measuring before you're sending any marble doing anything. Theta has to be one of the given knowns of this lab. It's the angle, like my pictures are trying to show you here. The theta that I'm talking about is the original angle of inclination, of elevation of the track as measured by the horizontal. Right? So the question is, where is your original known theta in this funky vector diagram that I just made? And the answer is, it's the angle at the bottom. It's not the angle at the top. Because the line at the top that goes along the plane is parallel to the plane. And the angle theta is a measurement between that line and a horizontal, not between that line and a vertical. So it can't be the top angle. I could say that again more slowly on Wednesday if you want, or you could send me an email or text or whatever. But I'm saying if theta means the original known angle as measured from the horizontal, then it is the bottom angle in this diagram, not the top. And SOHCAHTOA, sine is opposite over hypotenuse. So bottom line, I have to move on. Obviously, I have 2 minutes. Sine is not always X or Y. Sine is opposite and cosine is adjacent. But all right, so that's therefore, okay, I have to do this quickly. Therefore, the component diagram for the up situation is gravity is no longer there. Gravity now becomes sine and cosine. So I place them into the diagram. Sine goes along the direction of the plane with the friction. Cosine goes against. So cosine is supporting the normal force. Well, the normal force is supporting the cosine fraction of the weight, and friction's working with the sine. Okay, we've got 2 minutes left. So that's your component diagram for up. But here's your component diagram for down. Notice the one difference is the friction. Now it looks like, now friction's always opposing you. Friction's always opposing the motion of the marble. But the key thing that you can now see in these component diagrams is that when you're going up, friction's helping gravity. And so they're all working together. So the net force on the way up is huge. Therefore, the acceleration is huge on the way up. The magnitude of the acceleration is huge on the way up. On the way down, the friction's going against gravity. It's tiny. What I mean specifically mathematically, I'm doing this fast, obviously, but you'll see in the PDF. We now finally do F net equals MA along each axis one at a time. I know I have 1 minute left, but this is a procedure every time. Sum of all the forces in the Y equals MA times Y. So I look at the Y axis, normal minus mg cosine theta equals MAY. A is 0 in the Y axis. So the normal force in this lab is supporting the cosine portion of the weight. Why do I care? Because now when I go to the final step to the x-axis, I need that normal force to plug in for friction. This is it. And we have 1 minute left, but you could go like in the y-axis on the way up, gravity is working with friction together to make a huge net force, to make a huge acceleration, magnitude on the way up, but on the way down. This is the last slide. Okay. And I know it's 1:30. You can go if you have to go, but give me 1 minute if you can, or whatever. And then if there's questions, I'll stop. The only difference between the up and the down is that plus or minus sign, but it makes all the difference in the world. The magnitude of the acceleration on the way up is huge. The magnitude on the way down is smaller. What does that mean in English? On the way up, you slow down at a fast rate. You lose speed at a tremendous rate on the way up. When do you stop? When you've run out of speed entirely. So you're losing speed at rapid rates on the way up until you run out of speed. Then you come back down and you start gaining back speed at a slower rate, and you never gain back all the speed that you started with. On the way back up, you go run out, run out, run out, decelerate, 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 slow down, slow down, slow down, whoop, stop. On the way back down, you gain at such a slow rate that by the time you get to the bottom, you haven't gained back all that you started with. So the rate at which you lose speed on the way up, here's the punchline of the whole lab. For those of you who are still with me, the reward. The punchline of the whole lab is the rate at which you lose speed on the way up is bigger than the rate at which you gain speed back on the way down. So you never gain back all the speed you started with. So your average speed on the way back up is greater than your average speed on the way back down. That's it. It's the diagrams. It's all because friction flips and nothing else does. That's it. Thank you for being so patient and flexible. I'm hanging out for a second if there's any questions, but other than that, I'll see you Wednesday, I think. But cheers. Okay. Have a good day. Yes, thank you. Have a good day.